Shida. So we are here to today talk about Apache Spark on Hadoop and AWS, and we have distinguished Dr. Keith Stewart from AWS, solution architect on big data solutions, and also Adam Brindle, our in-house big data Spark consultant, who's going to run through the platform. Can you go to the next slide? Shri? So about the Stack Armor, so the Stack Armor is basically we are a cloud migration and the managed services with cybersecurity consulting firm. We specialize on automation and intelligent software systems. What we normally, what we try to differentiate ourselves is, we try to differentiate ourselves as cloud for business, where even though the cloud initially started as the infrastructure angle, but we take the business angle, and from there we lead our customers to a proper business use cases, and you would see one of that explanations, demonstration of those use cases on specific industries today. We are doing this from 2009. We have several CSAs, cloud solution architects with us. We have a very big competency on Microsoft when Windows workloads, including SharePoint and all the other databases. We have also, on the IoT competency, we are also doing a bunch of AWS-based IoT solutions for various customers. Can you go to the next one? So we are one of Amazon's AWS Advanced Partner, and this is basically the link to us. When Adam is going to do his session, he's going to do a small demo of how Stack Armor works and how you can bring your loads into a business case perspective into AWS. Can you go to the next one? So that's me very briefly, but let's go to the big data. I go to the next one. So basically how Stack Builder is, basically Stack Builder is stacking on top of the platforms or products which combinedly together solve a business use case. There are dashboards, there are data solutions, there are web applications, and there are a bunch of DevOps coordination need to happen during the development. What we make sure is we make sure that we hide all the factor of the standard cloud terminologies like CIDR block, what is the instance type needed for this, how the VPC should be built. We kind of abstract all those stuff using our IP created Stack Builder and spin those services needed on the relevant AWS instance types with security built into it. Based on use cases, either it could be HIPAA compliant, it could be FedRAMP compliant. We will spin those servers ready for those compliances. And if you go to the next slide, Shri, so basically that's the slide is the screenshot of how Stack Builder, Stack Armor, the Stack Builder of Stack Armor is going to be used. And one of the samples is, if you do the data analytics portion of it, for example, it'll walk you through what type of workload you need, what type of, how do you describe it, and how do you configure it, and how much is going to cost if you manage by yourself or if it's managed by Stack Armor. So those things will be kind of demoed a little bit by Adam in the next session. So I would like to hand over the session to Adam to take it over from here.
Thanks, Shida. Adam, I'll make you the presenter now. You can take it out from here. Give me a second.
All right. Want to make sure everybody can see my screen here.
Yes, Adam, we can see your screen.
So, excellent. So everyone should be seeing the main page. This is what it looks like when you first come to stackarmor.com. And so before I dive into Apache Spark, I want to just briefly show how quickly you can get an analytic cluster up and running in EMR on Amazon using Stack Armor. So from this main page, the first thing I'm going to do is just pick my region underneath. So I'm going to click on the American flag here because I'm in the US. And that brings me to the first part of this TurboTax style wizard that we were just talking about. So I can pick a stack for a particular kind of workload. In this case, we're going to focus on analytics. So I'm going to pick this option that has Hadoop and Spark and various other things like Cassandra and Tableau. Select that and go on to the next step. So from here I can do things like choose what scale of analytics I'm looking at operating, so what sort of, that'll help control what sort of cluster we'll be using. So I pick proof of concept. What kind of domains, sort of business domain specific security we might need, so financial, healthcare, government, and then the last part is whether I want fully managed or self-managed environment. So in this case, I'm going to pick fully managed and go on to the next step. And so here there's one main choice under select my stack where I can pick which particular tools if I have a specific idea of what I want. If I'm doing big data analytics using Spark, I would probably choose something like this option right here that says Big Data, Spark, Kafka, Cassandra, Hadoop. There's also a few other options that might be useful, like Apache Spark with EMR down below, but I'm going to go with the Big Data stack that has a bunch of commonly used Spark and Big Data tools. And then when I click Next Step here, I can choose anticipated utilization. So do I expect to be running this cluster 24/7, just business hours, or a little bit less? And I get some scaling and pricing information right here. So right on the screen, I can see roughly what kind of instances are involved and the cost. And from there, I can submit my information. So I can punch in my name, email, phone number. Click Submit My Request, and I'll get an email back from StackArmor very quickly with instructions and links to launch into my cluster. So it's really that straightforward. If I go ahead and launch a cluster that way and wait for the email to come back, if I choose one of the stacks that includes Spark and Zeppelin notebook tool, I can get directly into an environment that looks something like this, which I'm going to use for the rest of the webinar. So you can see right here, this is actually running on Stack Builder. So it says emr.zeppelin.stackbuilder.us. So this is a Stack Builder provisioned instance. And so we're running in Amazon Web Services using Amazon's EMR or Elastic MapReduce tool. And within EMR, we've got Apache Spark 2.1 configured. And we've also got the Apache open source Zeppelin notebook project set up. And that gives me a nice graphical interface that I can use to submit queries and visualize data with Spark. So that's a nice way to experiment and develop with Spark, and that's how we'll do the rest of the webinar this morning. So we've got about another 40 minutes or so to take a quick tour of many of the key areas of Spark. So I'm going to talk a little bit about that in a second. At the end, we may have time for questions. We'll see how we're doing on time. My name is Adam Brindell. I'm a consultant with StackArmor, and I also work independently doing instruction and consulting on Apache Spark, big data, machine learning, and deep learning related topics. My contact information is right here, so you're welcome to email me. Here's my address at Gmail, and I have a profile here at LinkedIn. And I have a picture of me from when I had a beard. So I do look like that, but if you looked at me right now, I'm minus the beard. So I'm going to scroll down here just a little bit. And what we want to see if we can cover in about 40 minutes is a little bit of background and architecture so we understand some Spark terminology. We'll do a little bit of querying data using the DataFrame and SQL APIs. To do some analytic queries with Spark. And then a very, very brief intro to Spark 2.x structured streaming. So this is a streaming API for continuous applications with Spark. And the last part, a very brief look at SparkML, which is machine learning algorithms and infrastructure that are part of the Spark API. So the very first thing I'm going to do is just make sure that all of my data is deployed here. And in the EMR environment, I've got HDFS set up. And that's actually going to work here as the default file system with Spark. So we'll see in a second that I don't need to do anything special to talk to HDFS. But first, I'm going to go ahead and list out my files, just make sure that the data is there by doing a %sh, which is a magic tag for running a shell command. And I'm going to go HDFS DFS-ls temp. And there we go. So just making sure that the data sets we're going to use, like the Amazon 20K, diamonds, and so on, are deployed. And then before we even talk about how Spark works, I think it's always great to just get directly into some code, especially if there's more technical folks on the line. You're probably saying, well, I want to get some idea of what this actually looks like running before I get into the architecture end of things. So we'll run a couple of queries, and then we'll talk a little bit about Spark. So the easiest way to just run an analytical query over some data is something like this next cell here, where I have a %SQL, select star from, and then I use this particular syntax Parquet dot and then a file path. So that's one of many syntaxes that you can use for accessing data. This is a really easy way to just point Spark at a file and say, here I've got some file in HDFS in Parquet format, and I want to run a query directly over that file without doing any additional integration or writing any extra code. So I'm going to run that cell, and it'll spin for a couple of seconds, and I should see some data start coming back. So this data set is an Amazon review data set. So what we're looking at here is, you can see there's a rating column. That's the number of stars that the product got in the review, and then the actual text of the review. So we might use this for analyzing distribution of reviews, or more likely the language that's used within reviews. So natural language analysis of the text, or maybe some sentiment analysis, that sort of thing. You can see we get a nice HTML table view. This is courtesy of Apache Zeppelin, that we can see get kind of a really nice format here. And if there was numeric data, we could go ahead and plot it. Maybe we'll take a look at that later. There's also a button for downloading. Of course, we have to be a little bit careful about what kind of data sets we're downloading directly. And you can also see that we're just seeing the first 1,000 records here. So we might have 1 billion records out there in S3 or in HDFS. We obviously don't want to bring 1 billion of them into the browser. So we've got a little limit operator there that makes it easy to write these queries. If we're not in a notebook environment, if I wanted to run this using just code, and this is Scala code, I could do it like in the next cell here, spark.sql, and then pass the same SQL query as a string. And if I run that, I get the same results back. The main difference is that it looks a little bit more like a command line database client. I'll get a little text view back. You can see what that looks like. I've got kind of a text table instead of the pretty HTML. And I can also use a domain-specific language to programmatically work with this inside of Spark. So if I don't want to use the %SQL, or I don't want to write SQL string literals, I can say something like spark.read.parquet to get access to a Parquet reader and point that at the file. So these are just different ways of doing the same thing, which might make more, sense in different business situations. Sometimes you want to be writing straight SQL queries. Sometimes you want a pretty report in a web page. Other times you're working programmatically and you want to get a handle to a data set to manipulate further. I'll write maybe 1 or 2 more queries here, and then we'll talk a little about Spark. So here's one that counts the ratings. So maybe we want to see how many ratings we have at each different level. So here we can see how many 1-star, 2-star, 3-star, and so on ratings we've got. And using these other little buttons here, I can switch to a graphical view. So I could do something like maybe create a pie chart. In this case, I probably want something like the rating as the key here, so I can see how the reviews are divided up. So There's a nice open source graphing widget, and of course Zeppelin is open source, so it has a pluggable infrastructure, and you can create additional different report views and add those into Zeppelin. We'll do one last query here. This one's kind of fun. Looking for reviews that contain the word awesome, but only got 1 star. So that just gets you some humorous results. You know, people that thought a product was going to be great, and maybe it didn't turn out so well. You might also be wondering, what kind of SQL can I actually use with Spark? Is this standard SQL, or do I need to write something special? So there's 2 main dialects supported in Spark. Spark will parse all of the SQL 2003 standard. So you can run your standard queries. I say parse because there are certain operations in SQL that don't make sense in Spark. Like, for example, inserting specific rows. If your data is actually a giant plain text file in S3, it may not really make semantic sense to be doing an insert, and so that operation might not be supported. But the syntax will all parse, and where the operators make sense, Spark will implement those. And we've also got support for HiveQL, which is a dialect of SQL that's designed for the Hadoop Hive project. And that's because Spark is designed to interoperate really well with Hive. So if your company has a big investment in Hive reports and Hive tables, you can query those directly from Spark, even using your existing HiveQL syntax. You can also create data sets in Spark and then expose those to Hive. So Spark is designed to play really nicely with Hive because so many companies use all the tools in the stack together. So now that you've seen a very, very quick introduction to writing some queries with Spark, at least over one particular data source, I'll give you a little bit of background. So what is Spark? Fundamentally, Spark is a distributed compute engine, so a distributed compute architecture. It's part of the Hadoop stack in terms of kind of where it lives in the big data world, but it's also a standalone project, so you can use it with or without the rest of Hadoop, either in an environment like Amazon EMR or wherever else you need to. Well, I guess EMR is Hadoop, but you could run it in Amazon without EMR if you wanted to. It was created originally in 2009 as a graduate computer science project at UC Berkeley. The latest release is 2.1, which came out last December. And sometime in the next few months, we'll see 2.2, which has a lot of new improvements. It's an open source tool under the Apache license. It's based on a data parallel architecture. So data parallel means that we take our large data set and we divide it up into a bunch of pieces, and we run the same code on different chunks of data at the same time. So we achieve parallelism by running the same code over different chunks of data, and these different chunks of data are usually in different places. So if we have a large cluster, we'd like to hopefully be using all of the cores and in the cluster kind of in parallel. Spark is also designed to support fault tolerance. So if we're running a really large clustered compute job, things will fail, right? So the infrastructure is not perfect, and if we have thousands of machines, we can expect certain failures to occur, whether it's network routing, whether it's a machine that goes down. And so we need to be able to not only continue our computation when some of the environment fails, but we need to make sure that when we catch up, that we catch up correctly so that we always compute sound results, and that we can catch up quickly, right? Because just because we have one failure doesn't mean that we won't get a second failure. So we need to catch up quickly enough that we don't have additional failures and we sort of fall behind. Spark is designed for high scalability. It currently supports workloads on a regular basis into the petabyte range, scaling up to about 10,000 nodes. Spark supports data locality aware scheduling, which means that Spark, in certain circumstances, keeps track of where the data is and will send the compute to the data rather than trying to move the data to where there are compute resources. This is really useful because in the big data world, moving the data around the cluster is very expensive and time consuming. So we'd like to send the compute, which is typically a very small amount of code, to where the data is. Load balancing, which we won't have a chance to talk about today, but that's the idea of keeping our utilization across all of our cores as close to 100% as possible, right? So we don't want to have a situation where a long-running program is using a few cores for many hours or days and the rest of the cluster is idle. So Spark will handle that. And over the years, Spark has been repeatedly re-architected, especially in the last 3 years, for 10x or higher performance gains. So big changes in the design of Spark so that we can get 10x or 100x performance improvements. The motivation for Spark was to leverage the availability of more cheap RAM and 10 gig networking, and to make less use of hard drives. So especially spinning disks, but even solid state disks are slower in a lot of cases than RAM and network. So Spark is designed to leverage RAM and network as much as possible. Spark, how is Spark different from Hadoop? Well, Spark is part of the Hadoop stack. So in some sense, it's part of Hadoop. When people ask this question, they usually mean, how is it different from MapReduce? So Spark is quite different from Hadoop MapReduce, which it has pretty much replaced now. And the key differences are a more general and expressive API. So SQL is directly supported inside of Spark at this point. It's not part of some kind of a bolt-on tool or converter. Long-lived executors and lightweight tasks. So we won't have time for that today, but that has to do with how Spark schedules jobs, and it's a very efficient scheduler. How is Spark different from relational databases? So in the early days, you would never mistake Spark for a relational database because you had to program Spark so differently. It's a little more confusing now because Spark has direct SQL support, and a large set of use cases for Spark are around analytical queries. So in some ways, it starts to look a little bit like an analytical database. But the big difference is that Spark does not own any storage, right? So if you are using an analytical database, the database owns and controls storage, organizes storage in order to optimize certain queries, and that also kind of constrains what you can do. Spark is more of a compute platform, so it will play well with almost any storage source, whether it's HDFS, S3, relational databases, wherever else data might be, but Spark doesn't control that storage directly. So that's kind of a quick background on Spark. We'll talk for a moment about the basic architecture. What are the pieces in a Spark cluster? So there's three main ingredients. There is the driver, which is a JVM or Java Virtual Machine, and the driver is kind of the brains of the operation. When you punch in code or a query, it's going to the driver, or your code in some cases is the driver. And the driver is the only part of the Spark cluster that really understands your query and can analyze it, optimize it, and control the workflow. So that's why I call the driver the brains. The next component are the executors. So executors are JVMs, and they're designed to be dumb. And the reason they're designed to be dumb is so that they're disposable, and when they fail, it's inexpensive to bring up new ones. So we might have a cluster with one driver and maybe 100 or even 1,000 executors, and the executors just execute tasks that are sent to them from the driver. They can also cache data and trade data with other nodes in the cluster. And then the last piece of the puzzle is a cluster manager. And the cluster manager is mainly used by the driver when it needs to get more executors, especially at the beginning of a program, or if it needs to scale the cluster up and down. So these are the key pieces, the driver and the executors. So how can we program Spark? So there's lots of ways to program Spark, which is one of the reasons it's so popular. We can work with Spark interactively, like I'm doing right now, using a notebook program or the built-in Spark shell. We can write scripts, typically in Python, and submit those against a Spark cluster. We can also compile programs using Scala or Java and run those, basically submit anything that we can bundle up into a jar file, and we can submit that and run Spark code that way. We can also use tools that would like to treat Spark as a JDBC data source. So maybe you have a reporting tool that has JDBC integration and you've got some queries you want to run. You can point that at an appropriate port on Spark and talk to it over JDBC. So lots of ways to do that. And lots of languages supported. So we've seen SQL and Scala already today. Python and R are also supported directly in Spark. Java, and then via the open source Mobius project, we have .NET integration, things like C# and F#. and various other languages. The main languages are Scala, SQL, Python, and R. So let's say we want to bring down some additional data and look at how we might work with data that wasn't kind of already prepared for us. I've got a data set here that I'm about to access, which is open source or a free data from the Wikimedia project. This is web analytics data from the presidential inauguration on January 25th. And I picked that because if you look at the page view activity on Wikipedia, that usually has some reflection of the news, of kind of what's going on in the world, and so it's sometimes interesting or informative to see what people are searching for when big events are happening, like the inauguration. So I can write out the path to this file in HDFS, and then if I have no idea what's in that file, I could do something like spark.read.text, which is going to create a data frame or query over that data. And then when I call show, what that's going to do is it's going to run that query with a limit operator and bring back just a few rows as plain text. So I can see what that looks like. A data frame is a query, but we often think of it as a table. In the same way that in a relational database, you might have a view, which is dynamic, but you talk about it kind of like a table, even though the view is really a query. That's a good way to think of data frames in Spark. So they're really views that can be composed, but we sometimes talk about them like they're a table. So this is the beginning of that data set. It looks like it's delimited by spaces here. It looks like I've got 4 fields, and they're delimited with spaces. So let's see if I can get Spark to parse this for me. So I'm going to come down here and go spark.read, and then pass an option with delimiter as a space. I'm also going to say infer schema true. Infer schema true is slightly expensive, but when I'm exploring data, it's an easy way to get Spark to take a reasonable guess at which columns are numeric, which ones are strings, and so on. And then I'm going to use the CSV parser. So anytime I'm parsing something that has a fixed token like a space to delimit the columns, I'll use CSV. And then what I'm going to do is I'm going to say create or replace temp view. So the first line creates a data frame or view called PC1, and then the second line says create or replace temp view, and what that's going to do is add an entry into the SQL catalog so that I can query this using SQL instead of having to use code. I can use either one after I run the cell. So we'll go ahead and do that. Most of this time is probably the infer schema, because that requires Spark to take a look at the data in order to figure out what types are present. And then we can go and query it. So I can do a select star, and now with just 1 or 2 lines of prep over an arbitrary file, I'm able to start running SQL, and I get something that looks like a table. So the next thing I'm going to do is I'm going to clean up this table just a little bit. So that first column is the Wikimedia project. Project are things like French Wikipedia, English Wikipedia, Wikibooks, Wikitravel. So I'm going to rename that first column to project. The second column is the name of the page that was loaded. So I'm going to call that column page. And to do each of these changes, I'm using this operator with column renamed. So with column renamed just changes a column. It gives me a new version of the data frame or query with the schema adjusted. The third column is the number of requests that happened, and this data is for a particular hour. So this is within a particular hour, the number of requests. And then I'm going to drop the final column because we're not actually needing that one. So I have a drop over here. And then I'm going to give it another table name with a create or replace temp view. And you can see Spark comes back and says, okay, you've got a org Apache SparkSQL data frame, and it shows me a little summary of the schema. And now I can do some interesting queries. So I can see, for example, how many rows there are. So how many pages were requested during that hour during the inauguration total. Let's see. If I do a select count, I can get the total. I'm sorry. Here I did a select star, so I'm just looking at the first few rows again. If I insert a count in here, then we can change that around. So it's completely interactive. I can just come in here and change the query, run it again. We can see how many rows there are. And it looks like there's 6.8 million. If I want to see the most popular pages, I could do something like order by request descending. We get something like this. So, not surprisingly, the articles on Donald Trump are bubbling up towards the top. And of course, the main page is usually going to beat out everything else. If I want to filter for just the English project, I can do that using standard SQL syntax. So I can say filter where project equals EN. And so we can see the top pages in the English project. And if I want to see the number of pages in the English project, I can look here. And this is not the number of pages that exist. It's the number that were queried. So this might give me an idea of how many queries were coming into the English project versus the rest of the world during that period of time. And last, maybe I want to see what the popularity of different pages was that included the word Spark. Right, so Donald Trump was probably the most interesting event at that point in time, but people are still querying for other things. So you can see Apache Spark got 40 requests, and there's also other things like the Chevy Spark and sparkling wine and so on that also got a few queries in that time frame. So as I mentioned, we can write all kinds of SQL queries that include SQL 2003 and HiveQL operators. And there's a domain-specific language that I'll demo in a second also. In this cell, I've got just a few of the operators. So the Spark documentation, of course, covers the dozens of additional operators that are supported. But this is what it looks like to use the most common things. From the SQL side, we have things like select, where, group by, order by, and join. And then in the programmatic API, they look pretty similar, and we can specify conditions using SQL strings or using column operations. So here in this next cell, we'll take a quick look at writing the same query using the domain-specific language for manipulating columns and queries. So we would say spark.tablePageCounts, which looks up the page counts table in the catalog. And then we can use a filter operator. So here's one of the flavors of filter that uses SQL syntax in this case to look for English project. Here's another filter for page like Spark. This uses a different syntax, and I mixed them up here just to demonstrate. You probably wouldn't mix these styles in your own code. In this case, we're finding a page column object. That's what the apostrophe page turns into. Like is a Scala method, and then we've got a parameter here, which is the Spark with the wildcards. And then similarly for order by, I'm grabbing the requests column using this syntax with the apostrophe, which is a Scala symbol that gets converted to an appropriate column object. And then the DESC here, it looks like it's some special operator, but really it's just a method on column. And this will perform the same query we just saw. So which syntax would you want to use in your own projects? It pretty much just depends on your business needs, right? So if you have end users punching in queries, it's nice to offer them SQL. If you're creating something that programmatically manipulates reports, you probably don't want to be manipulating those in SQL. It might makes more sense to use objects for the queries, columns, and conditions. So continuing on in our very, very quick tour of Spark, we'll talk a tiny bit about structured streaming. So structured streaming is the newest API for streaming applications using Spark. And it's based on this idea that the easiest way to reason about streaming is to not reason about streaming. And that's not really a tautology. What it's meant to express is this idea that in many streaming frameworks, including the older versions of Spark, the end programmer had to think quite a bit about the timing involved in manipulating streams. So when are records coming in, and how many are you seeing at a time, and how do you handle late records? And so the streaming and infrastructure became a big part of sort of the forefront of creating programs. There wasn't a lot of abstraction above the time-oriented ingestion of the data. So this new API is designed to treat streaming sources as append-only tables. So the idea is I write a program which really thinks about tables very much like a SQL program, And at any particular point in time, I have the consistency as if I'm operating on a strict prefix of the complete data set. So there's a semantic guarantee that's provided by the infrastructure, and as long as I use the right sources and sinks for my program, I automatically get exactly once execution, and I automatically get internal resilient state management for aggregations over time. What that means is if I'm doing some kind of long-running group by and I get records that are late or out of order, they'll end up in the appropriate groups, and I don't have to worry about that. That state where the aggregation is being tracked is managed for me by Spark. So let's just take a quick look at an example, also using, in this case, live streaming data related to Wikipedia. They actually publish all of their edits to the internet in real time. So first I'm going to run a drop just in case I had that table defined before. And then what I'm going to do is I'm going to read the stream of data very much like a table. So I'm going to say spark.readStream, and instead of saying something like format CSV or format JSON, I can say format socket, because this particular source is socket based. I'll provide options that list the host and port, and I'm going to go .load. And I get back something that notice it looks like a data frame. So this is a streaming source, but I treat it just like any other data frame. And the schema here is just a single string called value. But I happen to know that it's JSON encoded data that represents the real-time edits to Wikipedia. So in order to manipulate those, I want to parse the JSON. So in the next line, I can run code, which is, again, just like I would do over a static data frame. So this line here with lines.select and JSON tuple, this is the same exact code that I might use over a plain text file that had JSON data in it. I mean, if I knew it was JSON, I might use Spark's JSON parser instead. But the point is that I can manipulate this just like any old data frame and generate another data frame. So I'm basically doing ETL on a stream of data. And then, of course, if data is coming in, it has to go somewhere, right? So the idea of the streaming model is that we have sources, we have processing that we do on the stream once we've read it, and then we've got a sink that we're going to send the data to, so it has to go somewhere. In this case, I'm going to put it in a memory buffer so that we can build a little dashboard. Obviously, we can't store all of the data forever in memory, but we can make a little dashboard that way. So I'm going to call this thing demo. That will let me query it using SQL. I'm going to specify output mode append because I don't have any aggregations. That tells Spark that this is a little bit of an easier job to do, and it can optimize for that. I'm going to say format memory because I'm just going to be buffering the result. So we can query it, and then I'm going to go .start, and you can see it says streaming query demo state is active, and now I can query this. So these are real-time edits that are just coming in from Wikipedia. You can see we just got edits in the Italian, English, Spanish, and Polish, and Swedish versions of Wikipedia just in this first batch of data. And we can see various properties about them, in this case whether they're anonymous edits, robot edits, and when they happened. So let's say I want to make a dashboard here that allows me to track the number of edits in the different languages over time, which might be interesting to, for seeing what articles are popular for edits around the world, or where exciting things are happening around the world and are generating a lot of controversy or edits. So I can use the same domain-specific language and talk to the streaming table, just like a static table, spark.table demo. I'm going to do a group by, and I'm going to use Spark's built-in window function, which generates start and end window buckets, so I can aggregate data into these windowed buckets using, in this case, a 10-second window over the timestamp field. I'm also going to group by the channel or the language of Wikipedia. Then I'm going to do a count, and then I'm going to do a create or replace temp view, and that's going to update a table that I can query using SQL called counts. And then to get a nice report, I can select star, and I can also create a formatted version of the date that's a little bit prettier from that counts table. And that gets me, in this case, this really nice line chart that's showing me the edits over time. So if I wait a few seconds and run this, you'll see it actually updates. Right, so maybe a little bit hard to see, but it just updated and showed another 10 seconds or so worth of data. Maybe if I run it one more time, you can see I've got a little bit more data. So literally, 5-6 lines of code. I'm ingesting data, parsing, processing it, generating visualizations, using the Spark Structured Streaming API. So that's about all we have time for on streaming here today. I just want to, obviously I'm not explaining how this works, but what I'm showing you is just the flavor of what it's like to work with this particular API, and you can see, you get some idea of some of the tasks that it's designed to simplify. So I'm going to stop that query down here, and that gives us something like 5 or 10 minutes for the very last section, which is about Spark machine learning. So again, machine learning is, of course, a huge topic unto itself, from the math and the algorithms to feature engineering and so on. And of course, we don't have time to talk about all of that, but what I'm going to zoom in on here is what is it like to use Spark to run machine learning algorithms and build models. So I'm going to give you just a flavor of the Spark API. And in this case, we're going to work with a data set called Diamonds. This is a free data set that's part of the R programming language and the ggplot2 visualization package for R. It's a data set of about 50,000 diamonds. And for each diamond, there's various properties like the dimensions of the diamond, the carat weight, and so on, along with the sales price in dollars. So we're going to see if we can build a model that uses some of these features to predict the value or sales price of the diamond. So first thing I'm going to do is read this data into Spark. It starts out in this CSV file here, and I'm going to read this using infer schema true, which we talked about earlier. I'm also going to say header true. This particular data set has a header row, and the header row will give me a nice field name. So when I run this, the output will show me that I've got a data frame, and it'll show me a little bit of the schema here. So you can see that has the carat weight, which is a double, and a bunch more fields. This first one, _C0, that's a row number. We're going to throw that away anyway. In this next cell, we're going to select out a handful of features. So these are not all the features, but in this case, we'll play with just a few of them. The carat weight, the X, Y, and Z dimensions of the diamond in millimeters, and depth and table. Depth and table are numbers that characterize the shape of the cut of the diamond, so those might be important. And we'll grab the price, and we're going to rename the price to be called label, just because that's a default for a lot of the machine learning helpers. So we'll go ahead and select out those columns into a view called data, and then I'm going to create a split of 80% training data and 20% test data using the random split command, and then I'll destructure that into two data frames, one called training and one called test. And of course the idea is to build a model using the training data and then evaluate it using the test data here. So this is what the data looks like, just so you can get an idea of what this thing looks like. So we've got a table with mostly double precision floats here. Carat, X, Y, Z, depth, table, and label. Label over here looks like it's an integer at the moment, and it's in dollars. So how do we actually build a model? So of course the hard part is figuring out what features go in and what kind of model you want, and then tuning it. But the syntax is not going to be an obstacle. So my goal here is just to show you that the syntax of SparkML is pretty straightforward. So what we want to do is assemble all of our predictor variables, these are the ones that we're building our model on, into a vector. So all of Spark's machine learning algorithms are very uniform. They all take the same data types, and they all operate the same way. So although there are not as many algorithms in Spark as in, say, R, the ones in Spark are very, very consistent. So it's really easy to learn to use them and to experiment with different models. To take all of the values in these fields, carat, X, Y, Z, depth, and table, and put them into a vector, I'm going to use a built-in transformer called vector assembler. So I create one of those, tell it what the input is, tell it that I'd like to put the output into a new column in the data frame called features, and that will do the feature processing for me. In terms of algorithms, today I'm going to play with a gradient boosted tree regressor, which is one of the more higher capacity flexible models that's supported in Spark. This is similar to XGBoost, if you're familiar with some of the other implementations of gradient boosting out there. So I'm going to hold the algorithm here, and then I'm going to create a pipeline. And a pipeline is a abstraction that represents composing operations. So I want to take all of my data, I want to run it through this vector assembler, then I want to feed it to the regressor, and I want to package all that up to make it easier to talk about. In this case, there's only 2 operations, so it doesn't really buy me that much. But when you have a more complex pipeline with lots of processing, it's really handy to be able to create this pipeline object. This is inspired by the pipelines construct in the scikit-learn API in Python, although this one works a little bit differently. And I'm going to say set stages, and I'm going to punch in the stages to the pipeline. So first the assembler over here, and then the GBT regressor. And then in order to run the data through and actually fit the model to the data, I'm going to go pipeline.fit against the training data set. So we'll run that, and we'll see how long this takes. Obviously, if you have a large set of data, how long it takes to train will depend on the size of your cluster. In this case, there's not that much data, and we don't have that big of a cluster, so it'll take a few seconds to get this set up. And when we're done, we'll get a pipeline model. So a pipeline model is a resulting model that we get from fitting data against all of the pieces in this pipeline. And we've got a handle to this guy down here at the bottom called model. So how do I know if this is any good? I'm going to use the model to make predictions, and I'm going to use the test data set for those predictions so that we're seeing the behavior of the model against data that it has not seen before. So here we've got the resulting data frame test with predictions, and you'll notice that as we do these operations, we're always using data frames, and we just keep adding new columns to the data frame. So we don't have to create other data structures to manage our data. We get all of the advantages of the data frame optimizations that are built into Spark, and they underpin all of our machine learning operations here. So I've got my original properties, my feature vector, and now some predictions. So the predictions on the screen here, these don't look all that good. Maybe we need to get some statistics about the results so we have some idea how it's behaving. We can also call describe on the test data. So if we want to see some summary statistics, perhaps we want to see what the standard deviation was on the price, 3,900. So we have some idea, you know, how what our goal is. If we want to create a better model. And I can calculate the behavior of my model by using another class, in this case, regression evaluator. So Spark includes a set of evaluator classes, which provides the different sorts of statistics for different kinds of models. So in this case, because it's a regression project we're doing, we'll use regression evaluator, and that will get me metrics like root mean square error. So here I can see that my really quick and dirty GBT got me to a RMSE of about 1360. Comparing that to the standard deviation in the original data set, we can see that the model has extracted a good amount of information from the data. It's possible to do much, much better on this data set, so this is certainly not the kind of model you want to take and use to start your diamond pricing business. But it's a nice demonstration of how we can quickly and easily create a model with Spark, and then if this were a real project, we'd circle back and work on tuning it. So we're pretty much out of time. I don't really have time for Q&A right now, but I'm going to turn over the show to the next presenter. And hopefully this is a valuable look at how we can set up Spark using StackArmor, and then how we can use Spark for analytics, machine learning, and streaming applications.
Thank you, Adam. We have one question. How to configure Spark? Would you like to take that just one question?
That's a big question. How to configure Spark? So, yeah, I think that might be a little beyond the scope of what we can do here. I can tell you what the principal variables are. So when you're trying to configure Spark, and usually that means first figuring out how many executors you want and what size those executors should be. So how many cores, how much memory. The big variables are what kind of data are you working on? So how big is your data, and also what does your workload look like? And then from there we can get into more tuning. But yeah, tuning and configuring Spark is kind of a whole project unto itself. There's no really simple answers. It does require actually working with the data, and Spark has a built-in web UI which allows you to figure out how to tune the configuration. So you don't have to do it using log files. We could say try a particular configuration, look at the web UI, and that will tell us whether we are maybe having too many partitions of data or too few, or whether we maybe need more memory or other changes. But unfortunately, I can't get too far into it right now.
Thanks, Adam. Thanks very much for that. And also thank you for the session. It was really excellent. I hope there are no more questions. I think we can hand over the next session to Keith Stewart, Dr. Keith Stewart. Keith, I'll make you the presenter.
Okay. Let me know when you can see my screen.
Okay, you are the presenter now. Can you please click on the show screen? Yeah.
Yep. Can you see it?
Yes, we can see your screen. Thank you.
Okay, great. Hi, everyone. Thanks for joining. My name again is Keith Stewart. I'm a specialist solutions architect. I specialize in the EMR offering, which Adam mentioned. Adam went deep on Spark. I'm not going to go deep into Spark at all. I'm going to step back actually and talk about Amazon EMR as infrastructure on which you can run not only Spark but a whole host of applications. And what I'm going to do is explain why you would want to use EMR as opposed to other ways of deploying infrastructure. So what I'm going to cover, as I said, is EMR. EMR used to be called Elastic MapReduce. These days we tend to call it EMR because it runs much more than just MapReduce, of course, many more applications. So I'm going to talk about EMR, and in particular why we designed it the way we did, the features that it currently has and what we've recently added, and there's a number of important additions. I'll talk about use cases and design patterns, and then hopefully if we have time we'll get into some best practices as well. I'm not going to go deep into Hadoop itself, Spark or Parquet, HBase, or any of the other Hadoop applications. All right, if you only take three things away from this talk, these should be the three things. One, you should thoroughly appreciate that EMR does this decoupling of compute and storage, and that has so many implications, and we'll talk specifically about those implications, like choosing HDFS versus S3, data reliability and durability, implications for cost, implications for being able to run multiple clusters, and being able to support diverse teams, being able to logically separate the activities to support a diverse team. The second key point to take away is that EMR can be used for both long-running, or what's sometimes called persistent clusters, and short-spanned clusters, or transient clusters, as we call them. And the other thing is kind of a mindset. EMR enables you to think in terms of compute as a fungible commodity, not something that you have to purchase or to provision and own and be stuck with, but something that you can swap in and swap out and replace depending on your needs. So those are the three key points. All right, Hadoop, which is what many of the applications on EMR are part of, is Hadoop, is very popular among many industry verticals and among different applications. You see a bunch of them here: financial services, manufacturing, etc., healthcare, media, and we'll take a look at some specific examples as we go on. But when you are trying to deploy infrastructure for Hadoop, scaling it is a big challenge. So if you have, say, an on-prem cluster, which is what this icon is supposed to represent, you have a major challenge when you try to scale that. One option is to move to the cloud and spin up a fleet of EC2 instances, and then manage that yourself. Look after the individual EC2s, monitor it, replace failed EC2s, etc. That's one option, but it's a lot of work. And then what we're going to focus on is EMR, which actually is a managed Hadoop framework in the cloud that raises the abstraction level of what you're thinking about and working with to a cluster. So you think in terms of a cluster and maybe the size of it, and that's it. The rest of it is looked after as part of the managed framework. Okay. So specifically, what is EMR? It's a hosted service. You can run Hadoop, Spark, and many other distributed compute frameworks in the cloud. It makes it easy to quickly and cost-effectively process petabytes worth of data. So EMR is the largest cloud-operated Hadoop infrastructure in the world. Since 2009, when it was first created, there has been literally tens of millions of clusters spun up on EMR. Now, keep in mind, most customers are using transient clusters, and we'll go into details about what those are. But literally tens of millions of clusters have been spun up since 2009. This is just a small sampling of the many customers that are using EMR, and you can see some of them are very large household name type companies. If you want to, this is really, I'm not going to go through all the details here, but I just want to make you aware that if you want to drill down into lots of detailed case studies on the big data infrastructure on AWS and how customers are using AWS for big data, including Hadoop, you can go to this web page. aws.amazon.com/solutions/case-studies/big data, or just Google for AWS big data customer success stories, and you'll come to this web page, and you'll be able to scroll through here and look at specific companies. Each of these blue titles are clickable and will take you into the details of the case study, and you'll see there's lots here with some very big name organizations. And again, I'm not going to dwell on these, but you can see NTT Docomo, very large, etc. Okay, so you can check out that web page. So the question is, why have so many customers chosen EMR? There's 6 key reasons. First one is it's very easy to use. It literally takes just minutes to spin up an EMR cluster. It's low cost. You only pay for what you use. You pay by the hour. And Elastic, you can expand the capacity to, you can expand or remove capacity to suit or to right size the compute for the workload that you're doing. It's reliable. EMR monitors the cluster. If any node in the cluster dies or becomes really sluggish, EMR will automatically replace it with a new one, and it'll automatically balance redistribute the jobs across the new nodes. It's secure, so you can establish end-to-end encryption. You can have your own isolated part of the cloud to run EMR clusters and so on. And it's flexible, so you own the cluster. I mean, you have root access to all the nodes on the cluster. You can customize it the way you like, and we'll see examples of all that. So additionally, why EMR? So a key part of it is the automation. It relieves you of a lot of the work of deploying and monitoring and provisioning the cluster. The other thing is it's one of the most current, perhaps the most current distribution of Hadoop available. We're typically 3 to 5 weeks behind when the open source software becomes available, and we have a very, very rapid cadence and have some of the most up-to-date versions of Hadoop applications within the EMR system. It also has an interesting architecture, which we'll drill down into a little bit, which is this really distinct distinguished feature, this decoupling of storage and compute, which gives you a lot of flexibility to adapt things to exactly what you need and to minimize costs. And the integration, so EMR can talk to a wide variety of AWS services and be able to pull data in and output data, and you have the large numbers of AWS services that you can take advantage of. On the automation, so all aspects of the life cycle of a cluster are taken care of, including the provisioning of the member EC2 instances in the cluster, the configuring or the setting up the communication, designated master and slave nodes, and setting up that cluster communication, configuring Hadoop, getting all the right parameters in place, installing whatever applications, Hadoop applications you want or need on your cluster, and submitting jobs to the cluster and capturing results, monitoring and failure handling as I measured. All these steps are fully automatable with EMR, including at the end terminating the cluster if you're done using it. All right. As I said, you can run a whole host of Hadoop applications. So Hadoop is a very rich system, and you can see, and it keeps evolving. There's lots of applications available. Any of these applications can be deployed on EMR. If you go to the AWS documentation website for EMR, you'll be able to see with each new release, we show you what version of different Hadoop applications are part of that EMR release. And so you can go in and see those. If you zoom in when you're at the web page, you'll be able to see things like this that indicate how current we are on the different versions. This is an old slide. We're up to EMR 5.4 now. All right, I'm going to talk a little bit about the architecture of EMR. Kind of at a high level, EMR comprises the compute, and then it's got some UI capabilities on the right here as well. So at the lowest level is the ability to interact with a variety of storage mechanisms. So Adam showed an example of HDFS, but S3, using a component built into EMR called EMR-FS, allows EMR to interact with S3 as well. And you'll see soon in the next few slides why S3 is such an important resource to take advantage of. Yarn, which manages the executors, the resources on the cluster, and then there's a whole bunch of different ways you can do compute. You can do batch, you can do interactive, you can do in-memory. These are just examples, and then a bunch of sample applications on top of that. You can also run HBase, which is a NoSQL database running on top of Hadoop. But using Phoenix, you can actually provide a SQL layer that allows you to interact with HBase using SQL. And Presto is something you should definitely take a look at. Presto gives you an in-memory SQL engine, high-performance ANSI SQL engine that works on data in EMR and gives you very high performance, very high compatible ANSI compatibility SQL queries. And then you have ways to interact with the cluster, through using a variety of notebooks, Zeppelin, Hue, Jupyter can be deployed as well, Ganglia for monitoring, and then the Hive server, you can access the JDBC or ODBC. So here's this decoupling and why it's so important. So it's very different than on-prem or even deploying your own fleet of EC2 and EC2 instances and running Hadoop. EMR decouples the storage and the compute. So in a traditional deployment or an EC2 fleet, you'll deploy nodes, but those nodes will be tightly coupled in terms of the compute and the storage that's available. What that means is that when you try to expand it, you're going to have a lot of inflexibility, and we'll see what that looks like. EMR, on the other hand, decouples storage and compute. That gives you flexibility both on the storage side and then on the compute. So with S3, it's an elastic store. It's a massively parallel object store, and you can that will grow to accommodate whatever data you send to it. You don't need to pre-provision any storage. And then the right sizing means you can pick the appropriate EC2, the amount of compute that's appropriate for the workload. And unlike a Hadoop cluster where you typically have 3x the storage as compared to your data, because you need a three-way replication of your data for fault tolerance. With EMR, you only need enough compute for the actual processing. S3 takes care of the replication and the durability. So you're freed to pick the right amount of compute. All right, so as I said, with the on-premises or the fleet of EC2s, these are tightly coupled, and if you need to expand your capacity, you wind up adding nodes. And what that means is the storage that's associated with each node grows along with the compute, even if you didn't need extra storage. If you need more compute, more cores and RAM to process the data more quickly, you're going to wind up paying for the extra storage. Similarly, if you're mostly interested in storing more data, you're going to be paying for compute, extra cores and RAM that you may not need. But the key thing is compute workloads vary substantially. Here's an example of an on-prem Hadoop cluster showing kind of the utilization, which is the y-axis, over time. And what you'll see are cycles of week peaks. You'll get a little bit of data here. Then you may have some historical data set that needs to be reprocessed. It'll return then to steady state and with a bunch of other repetitions of that. What that means is this gray area is the excess that you've had to provision, because you're going to provision capacity, both storage and compute, for the largest workload that you anticipate, right? And for the SLA that you're obligated to fill. So that means that most of the time, possibly 80% of the time, you have excess capacity on your cluster that's not needed, right? You only need the dark blue stuff, okay? All right. Also, in an organization, there's typically a centralized on-prem Hadoop cluster, and you're going to have different groups and different workloads trying to run different things, and they're all contending for the same centralized resource. So some group might want to use Hive, someone might want to use MapReduce, others might want to use Spark, and you can see there are different kinds of workloads. Hive is compute bound, whereas Spark is a memory bound. It's an in-memory compute engine. So you've got different requirements of your infrastructure all contending for this centralized resource. Okay? EMR is very different. So with EMR, you aggregate all your data in S3. You treat S3 as your data lake, and that then gives you the flexibility to use a variety of compute. Remember, we talked about fungibility of compute. So you can have your data in S3, and EMR can read and write directly with S3. It's not copying the data first, and then it's not copying it to HDFS and then working with it. No, it's reading and writing directly with S3, and it's treating S3 as a Hadoop compatible file system using the EMRFS component. But when your data is in S3, if you're using S3 as your data lake, you've got all these options for where the data can go and how it can be processed and accessed in the future. So you're future-proofing your data when you move it to S3. Okay? So the advantages of S3 is you can decouple the compute and storage. This means, for example, that you can shut down EMR clusters with no data loss. So if your input records are on S3 and they get processed by EMR and then the results get written back to S3, you can shut down the cluster at the end of the batch processing and you've got no data loss. As I said, you can right size the cluster. So different groups will have different needs. One group might be a small data scientist group, maybe as small as a single individual. That group can have their own a cluster that could be a small size, just large enough to test an algorithm or to iterate on an algorithm. Then you might have, say, a software QA team that needs something approximating a production size, and of course you'd have a production size. You might have different departments with different needs, etc. They can each choose an EMR cluster appropriate to their needs, and each of those can concurrently work with the data in S3 at the same time, because you've separated the compute and the storage. So it gives you a lot of flexibility in how you can work with your data and how different groups can work with them. And as we said, multiple clusters can concurrently access it. So HDFS is still there, as Adam showed. HDFS can still be relevant if you're doing iterative workloads where you're making multiple passes over the data, and if you need to touch the data set more than once. But you can also do Spark and with the RDDs, resilient distributed data sets, data frames, etc., to do in-memory processing to avoid that. If you've got a lot of disk I/O workloads, that's where HDFS might have some advantages. You can persist your data on S3 and then use a tool. We have a version called S3 DiskCP to move the data to HDFS if you want to use HDFS for the processing. Now, keep in mind that companies like Netflix have done very careful quantitative analyses, and I would encourage you to Google for this, where they compared the performance of Amazon S3 and HDFS, and they found a negligible difference in performance, maybe a 10% difference in performance. The reality is most Hadoop workloads involve streaming data from the data store, the persistence into the cores of the cluster, and not random seeks and reads and writes. It's not a so latency is less of an issue, and it's more the streaming. And so whether the data is streaming from S3 or streaming from HDFS, it's still streaming. Okay. All right. You can take advantage of spot and reserved instances to lower costs. Spot instances are excess EC2s that have not yet been claimed by customers. We allow customers to bid on them. You can often get an up to 80, sometimes even 90% discount on the hourly rate for the EC2 instances compared to on-demand. Reserved instances just means it's an accounting mechanism. You put money up front indicating a commitment to use a certain number and type of EC2, and so you'll get a discount for that as well. So you can take advantage of all those. Here's some recent additions within the last few months to EMR. The first one is a big one. So S3 storage mode for HBase. So HBase, as I mentioned, is a NoSQL database. It's very popular. Previously, you had to run HBase with HDFS storage, local storage on the nodes, and we've now decoupled that recently, and that's proven to be very popular. We have examples of production uses of this already. FINRA is and they regulate the financial industry and literally deal with billions of transactions a day. They have HBase using S3 as the storage backing, and that's in production. These are the latest versions of Hadoop applications we have, a good number of them. We've got, and I'll show some other ones, I guess, as well. Some interesting ones. So we're current with Spark. As I said, we're typically 3 to 5 weeks, only 3 to 5 weeks behind the open source releases. HBase 1.3. This is an interesting one to take a look at if you have a chance, is Flink. So if you're doing real-time processing, Spark streaming is an option, but keep in mind that Spark is architected first and foremost as a batch processing framework. Now it can do streaming, but in reality it's micro-batching, so it's taking short time windows and moving them through Spark. So streaming is a secondary feature of Spark. Flink is the flip of that. Flink is first and foremost a streaming processing framework that also happens to do batch as a secondary type of workload. So if you're primarily doing real-time streaming, you might want to look at that. We also recently added some new instances, M4, which are the mainstream. They have a balance of RAM cores and disk, and so they're new additions. They give you more capacity. R4s are RAM or memory optimized, and these give you, it turns out to actually be a better price per gigabyte of RAM, and so they're a better deal in terms of the RAM. They also can give you large numbers of cores. Okay, instance fleets. This is something new as well. This gives you a lot of flexibility to optimize kind of the cost performance of your cluster. You can specify before you launch a cluster a list of up to 5 different EC2 instance types. So you show flexibility in the type of EC2 instance types you're willing to use. And then you can indicate you want a mix of on-demand or spot instances with your bidding, what your bidding is for the spot instances, and then the weightings, what kind of numbers of these instances are you looking for. And then using that, EMR, when it spins up your cluster, automatically provisions based on what you've indicated as a preferred capacity. And it'll try to use on the spot instances as best it can to save you money, and basically makes it easier to get this up and the cluster up and running at a more affordable manner. Okay, what do you need to run a cluster? Very quickly, 3 steps. You choose the instance types, you choose your software that you want deployed on the cluster, and then you choose how you want to access it. So you have these types of instances to pick from. They're in families. We have our general, the M4 should be in here. This is an old slide. They're good for general workloads like batch processing. CPU optimized if you're doing a lot of machine learning or statistical calculations. Memory optimized is great for Spark and for interactive applications. And if you're doing a lot of disk I/O, you can use disk I/O optimized instances. We have 17 applications today that you can have deployed automatically and configured automatically on the EMR, and we continue to add to those as time goes on. Anything not there and available with a single checkbox or a parameter call, you can deploy any Hadoop applications using bootstrap actions. These are bash scripts essentially that execute when the cluster comes up, and on GitHub we have a repository where you can grab these bootstrap actions for a variety of different applications. There's actually four different ways you can deploy EMR. You can use the web console, which is what most people use when they start out. You can use the command line. So if you want to automate the deployment, put something into a bash script, maybe put it under cron control or some other trigger, you can specify everything you need in that cluster on the command line and using the AWS CLI. So you install that on any kind of remote laptop or on a node, an EC2 running within AWS. And then finally, you can use our software development kits in a variety of languages and write your own UIs, your own applications that hide your users from the details of launching, configuring and launching. You can monitor the cluster, so you can use Ganglia. It's one of the applications you can install, and it'll give you real-time performance information about what's going on. You can debug all the logs from the runs from all levels of the stack, from EMR, from Yarn, from Spark, from Hadoop, etc., tasks and jobs. All those logs are captured and put on S3, so that even if your cluster, for whatever reason, goes away, you still have those logs accessible to you to review. Right, and you can specify where you want those to go, and you can visualize them. One key attribute of EMR is it's dynamically resizable. So you can start out with a small cluster, and then if you're looking to get a higher or faster completion of a job, you can tell it to dynamically expand its size, and it will provision the new nodes, and as soon as they're up and running, redistribute the work across those. That way you can match the compute with the demands that you have, and it works both ways. So you can take a large cluster and shrink it down to something small, kind of a minimal cluster that you could later resize up if you wanted to. We talked about spot instances. Yeah, you can save money there. Variety of ways to submit jobs from off the cluster. You can use the STEP API that's on EMR and submit things that way. Submit things, say, to a Spark application using our serverless compute. AWS Lambda, you can have Lambda send that to EMR. You can leverage a bunch of orchestration tools like AWS Data Pipeline or some of the open source ones and be able to submit things that way. On the cluster itself, you can have on the master node have a variety of web applications that can be exposed and made available, and you can have different dashboards and ways to interact through the web with that. Okay, I think we're maybe a little tight on time, so I'm thinking I might skip the security and move on to some design patterns and case studies, if that's okay. I can basically tell you that EMR gives you the ability to achieve end-to-end encryption. And there's physical isolation of the in virtual private clouds and public subnets or private subnets, security groups, etc. There's lots of options for how you can secure your EMR clusters. You can also specify a security configuration as a one-time effort and reuse that in all future EMR clusters if you like. And you can create multiple configurations if you like. So very quickly, some design patterns. This one is the simple batch processing one. So you've got a large influx of logs that get pushed to S3. Again, your data lake, push data there, say on a daily basis, and then you run a daily batch processing job that reads the data, crunches it, and then writes it. It could transform it, etc. Yelp's a prime example of this. This example. Long-running clusters, so again, data goes to S3, and you can have then the same thing, the daily EMR job or multiple batch jobs that process that data, but once it's in S3, then the data could be used by HBase to provide real-time dashboards with high concurrency using the NoSQL querying of that data. Number 3, interactive queries. So again, data comes into S3, and then declaring the existence of that data in tabular interpretation with the Hive metastore, you can use a variety of interactive query technologies to be able to work with those. And Presto is a key one, and you saw Adam use Spark for that. Netflix is a key example of that. They have on the order of 30 petabytes of data sitting in S3, and they work with, there's over 400 people using Presto to interactively query that data with SQL queries. Streaming data, so data comes in throughout the day. You've got a steady stream of data that's captured by Kinesis, and it can be fed to downstream processing applications or Lambda, but it can also be fed to EMR clusters where you can do some stream processing. Flink's not shown here, but it should be shown there. Okay, how are we doing on time? Are we running out of time?
Yes, you can just finish off this last slide, and okay. we can take a few questions now once you are done with that.
Okay, this slide simply summarizes the Spark, just some of the many customers that are using Spark on EMR in production. Those are well-recognized companies. NASDAQ, they're using pulling data in and doing ETL, feeding it to Redshift, but they're running Presto on EMR, supporting SQL clients. Washington Post, they have obviously they have clicks coming in from readers, and they have content that's being you know, they're doing a correlation between clicks and content, trying to segment customers to figure out which ones to send the appropriate ads to, and they can make recommendations, etc. Companies like GumGum, same sort of thing. So you know, they're an ad display platform, and they're using Spark running 24/7. But they, at the same time, they're running on a separate cluster, batch process, actually multiple clusters, and feeding Redshift, which is our data warehouse technology. Hearst, I won't belabor the point. Okay, so I guess we're out of time in terms of getting into best practices, and I'm guessing we want to take questions.